Thank you everyone for turning up to the final lecture in the Language Models and Intelligent Agentic Systems course, which is the future of language models. I was at a party recently and happened to meet a senior person at a well-known AI startup in the Bay Area. They volunteered that they thought humanity had about a 50% chance of extinction caused by artificial intelligence. I asked why they were working at an AI startup if they believed that to be true. They told me that while they thought it was true, in the meantime, I get to have a nice house and car. Michael Nielsen, Refractory Remarks on Oppenheimer. So what did we cover last lecture? So last lecture, Jason went through the different organizations that exist within the AI ecosystem. So these are both organizations developing frontier AI and those who are trying to mitigate the risks from frontier AI. And he went through various different categories of these orgs, including governmental bodies, such as National AI Security and Safety Institutes, such as the UK AC, frontier companies, the ones we care about the most, probably OpenAI, Anthropic, Google DeepMind, and also Meta, policy and governance think tanks like GovAI, RAND, CSET, and non-profit research orgs such as Redwood, Meta, whose work we've seen plenty of times throughout the course, FarAI, and Apollo. So what are we going to cover today? Well, today I'm going to talk a little bit about how we can try to predict the progress we expect AI to make within the next few years. We're going to approach this from two different perspectives. One perspective we're going to look at this is in the progress and the effective compute that we have access to training these models. And one is just from a straightforward, okay, how much economically valuable labor do we expect to be able to get out of these models as time goes forward? I'm then going to talk about a concept called an intelligence explosion that you might have heard before. And I'm going to deal with various objections or criticisms to the view of progress that I put forward in the first part of the lecture. I'm finally going to talk about superintelligence, so artificial systems that are far more capable than any individual human. And lastly, I'm going to talk about direct action that can be taken on these problems. So let's get started with predicting AI progress. So I'd like to sort of get you to cast your mind back to the days of 2019, when the best language model that we had at that time was GPT-2. And at the time, GPT-2 was remarkable for its ability to basically string sentences together and stay roughly on topic. So it could construct sentences that were roughly grammatically correct and able to stay within a certain topic or domain, albeit saying a lot of things that were false or nonsensical or making inferences that weren't logical. And so the kind of intelligence that we got out of these systems was kind of comparable to that of a preschooler. Basically able to talk with some coherency, but the best thing you could get out of it was a kind of nice story. Then in 2020, GPT-3 was developed, and soon after that, ChatGPT was released, demonstrating the capabilities of these systems to do economically valuable labor for the first time. And in terms of the amount of effective compute that was used to train GPT-3, it was about 2 orders of magnitude. So an order of magnitude here is a 10x increase. So 2 orders of magnitude means roughly 100 times as much compute was thrown at GPT-3 than was thrown at GPT-2. And the GPT-3 could write you bits of code that were often buggy, but sometimes would run or do the thing you asked. It could summarize documents for you to a reasonable extent, answer basic question answers, and sort of the level of intelligence that we're working at here is maybe that of an elementary schooler. And then a year after ChatGPT is released, we got GPT-4, which was another 2 orders of magnitude over 3 again. So again, 100x increase in the amount of effective compute thrown at this model to train it. And the intelligence we saw from that was roughly that of a smart high schooler. And now we have models like Claude 3.7 and Claude 4 that can really do a substantial amount of economically valuable labor autonomously, in the sense that you can give them coding tasks, and they will go and pursue those tasks by themselves, and often are able to write remarkably good scripts. It's often the case that you'll get this code, and within 15 minutes of debugging, you can have thousands of lines that work coherently and do the thing that you asked for, taking a fraction of the time that it would have taken you to write that code yourself. So here's sort of the central organizing question that we're going to address in today's lecture. How far is it until we get systems that are as intelligent as and as capable as ML PhD graduates? So people who have done a PhD in machine learning. Okay? So it takes 2 orders of magnitude to scale from something that's roughly as intelligent as a preschooler to something as intelligent as an elementary schooler, and another 2 after that to go to a smart high schooler. I'd contend the systems we have nowadays are at least comparable to smart undergrads. Okay, so how many more orders of magnitude on top of the systems that we have nowadays does it take to get to systems that are as intelligent as somebody who has a PhD in machine learning? So think about these frontier models, O3 from OpenAI and Claude 4 from Anthropic. Think about your experience with them and ask yourself, how many orders of magnitude away, so how many times do I need to scale up the compute by a factor of 10 before I get to the level of a competent machine learning PhD graduate? And I actually want you to think about this question. It's not rhetorical. I want you to think in your head about what you think the answer to this is. And if possible, come up with a 95% lower, a median, and a 95% upper bound, right? So you probably have some uncertainty about the answer to this. There's no good way of knowing. It doesn't, it's not immediately obvious how these models are going to get smarter as you scale them up. But given the uncertainty that you have, what is your median estimate? What's your 95% lower and 95% upper bounds? My claim is something like, well, 5 orders of magnitude, so that's a 10,000 increase in the quantity of compute. The 5 orders of magnitude on top of the same compute would be a very reasonable median estimate. But I'm actually not going to try to convince you of this, or I don't need you to accept this as a premise for anything else I'm going to say subsequently. Instead, the thing I want you to accept as a basically reasonable claim is that you would have to be extremely confident, you would be very, very confident to say that there was not at least a 5% chance that 5 orders of magnitude was sufficient. To say that you have over 95% certainty that 5 orders of magnitude wouldn't get you to a smart ML PhD, right? So my claim is something just like, there's at least a 5% chance, at least a 1 in 20 chance that 5 orders of magnitude, which is a 10,000 scale up from the current systems that we have, would be sufficient to get you from Claude 4 to a competent ML PhD graduate, right? So that's the only thing I want you to take away from this slide. Okay, yeah, question?
That seems really weak. Is that your actual median estimate? Or like?
No, I just want to start from a place where we could probably all agree. So people will generally disagree about how many orders of magnitude it takes, but I think that you can even people who are skeptical of current progress probably have enough uncertainty to say, yeah, there's at least a 5% chance that 5 orders of magnitude is sufficient, given that 4 orders of magnitude gets you from GPT-2, which can basically just string sentences together, to GPT-4, which can automate a lot of small coding tasks, right? So it doesn't really matter what I think, because what matters is what you think. And I just want to try to convince you that, yeah, you should probably think that there's at least a 5% chance that this is sufficient. So let's talk about what drives progress in AI at the moment. So I'm going to decompose progress in roughly the following ways. And this decomposition is taken from an essay called Situational Awareness, the Decade Ahead, and I think it's a fairly good one, which is compute progress, which is over time, we're just throwing more compute at these models, right? So we're just increasing the amount of money that we're willing to spend on larger and larger compute clusters to train these models. The second is algorithmic progress, that we get better and better algorithms for training the models. So effectively better payoff for the compute that we invest. This includes things like better optimizers, better architectures, things like that, right? And a large part of the recent boom in AI progress came from the discovery and the innovations of the transformer architecture, which would count as part of algorithmic progress, right? We didn't just throw more compute at models, we found a better way to throw compute at models. And finally, unhobbling progress, which is being able to better use the models that we obtain for economically valuable labor, right? So actually turning these systems that ultimately are trained on objectives that usually aren't relevant to economically valuable labor into something that you can get work out of. So let's talk first about compute progress, and let's look at historical trends. So I already addressed this in the third lecture on neural scaling laws, so I'd like to revisit that today. So compute progress refers to increases in the amount of compute used to train the model, and this can come from either better, cheaper hardware, so the cost of chips falls, and it's well known that the cost of compute falls over time, and we get better and better at making more compute for the same amount of money, or increasing investment. So the amount of money that a company or government is willing to expend on a single model also increases. And this has also seen reliable increases in time, that the amount of money that companies nowadays, OpenAI and Anthropic, are willing to burn on training a single model would have been unthinkable around 2000, right? I'm going to bring up this slide again, which is illustrating the relative parameter counts of these models, so GPT-1 through 4, and how these grow over time. And that this growth is due to willingness to invest larger and larger amounts of money in the models themselves, as well as increases in the efficiency of that compute. So let's recall this graph that I showed earlier in the course about the amount of compute used to train models over time. The important things to notice are, first of all, logarithmic y-axis, right? And logarithmic progress or exponential progress is sort of going to be a common theme throughout this lecture. So we're looking at, over time, the increase in the amount of compute increasing in an exponential manner. And in particular, pre the deep learning era, so pre-2010, the increase in compute goes up by roughly 1.5 times per year. So I have roughly 1.5 times as much compute being expended on models year after year. And then we hit the deep learning era, and we find a way to throw compute at models in a way that the models will just soak it up. You can always just throw more compute and get better models. And this puts us in a new regime where the investment that comes from throwing compute at models really pays off much better. And as you see, you might not be able to read it, but there's a 4.6x per year there. So we have a significant increase in the rate at which the compute being thrown into frontier models is increasing. And this is, so 4.6x per year is roughly 0.65 orders of magnitude a year, right? So roughly 0.6 of a 10x increase per year. Moreover, this is actually an underestimate. So the estimate I'm giving you of 0.6 orders of magnitude a year is actually pretty conservative, because if you restrict yourself just to language models, so you ignore all of the other categories and just look at language models, the increase in that case is 6.6 times per year, or roughly 0.8 orders of magnitude per year increase in just the sheer amount of compute used to train the models. So you might be able to see there's a 6.6x per year there. So the amount of compute we're throwing at language models specifically is increasing at an even faster rate than all those other models. But let's take the conservative estimate. Let's just go with the 0.65 per year. Okay, what about algorithmic progress? So this refers to better algorithms for those AI models. And this can be decomposed into better architectures. So both the discovery of the transformer architecture as opposed to LSTM networks, better activation functions, various tricks like residual connections and layer norms, all of this stuff, right? This counts as algorithmic progress for better architectures. Next is better training algorithms. So in this, I'm going to count things like better optimizers, so Adam and Adam W, better reinforcement learning algorithms, so PPO, all that kind of stuff. So better ways to use that compute to train. And lastly, better data sets and training objectives. So having higher quality data, being able to do RLHF and knowing all the tricks that are necessary to get RLHF to work. Also going to count this as algorithmic progress. So it's a little harder to measure this because you can't just go out and stick a, just count how many flops was used to train a model. You have to do something clever. But roughly, you can ask the question of, okay, if I knew all of the tricks that I know now, and I have the same compute as someone back at a certain point in time when they had a frontier model that used all of the tricks at that point, how much better can I do, right? So in other words, I'm trading off the amount of compute I have for the, the new knowledge and the new tricks that I've gained in that time, and I want to see where it equalizes. So if you're interested in how you do this in a rigorous manner, there's this great paper, Algorithmic Progress in Language Models. This is, again, from Epoch, which is the same organization that released the other graph, so they're really great for this kind of stuff. And they sort of decompose, okay, since 2014, we've had progress both in physical compute scaling, and algorithmic progress. And they decompose it and they look at how much has come from each, with roughly 7 orders of magnitude coming from compute scaling and 4 orders of magnitude coming from algorithmic progress. So in the paper, they say, we estimate that the compute required to reach a set language modeling performance has halved every 8 to 9 months on average since 2012. Right? So if we take the conservative end of that and take a 9-month doubling time, what does this amount to? Well, this is roughly a 2.5x increase in effective compute, so basically the gains that you get from your compute per year, or roughly 0.4 orders of magnitude a year. Right? So again, on the conservative end of things. Okay, so putting this together, how can we go from estimates of how many orders of magnitude of effective compute scale-up we need to estimates of when we would expect to see AI systems that are at least as competent as an ML PhD graduate? So conservatively, again, taking sort of the lower bounds of these numbers, you expect at least 0.6 orders of magnitude increase in compute per year, and 0.4 orders of magnitude increase in effective compute from algorithmic progress. So basically how much you're getting for having new algorithms. So again, putting these numbers together, you come to 1 order of magnitude in advancement per year at least. Right? And so this gives you a very quick and easy way to convert from your estimates over how many orders of magnitude you need, so your 95% lower, median, and 95% upper confidence range, to confidence ranges over how long it would take to reach that point, right? And so you can do this operation mentally in your head and just think to yourself, okay, given the order of magnitude estimates I came up with 2 slides ago, what are the estimates that I have now for the timeline, the date at which we reach these performances? And again, the only thing I really want to convince you of is that you would have to be extremely confident to think that there was not at least a 5% chance that by mid-2030 we have ML PhD graduate level AI systems. So again, if you think that there's at least a 5% chance that 5 orders of magnitude is sufficient, then you should think that there's at least a 5% chance that by mid-2030 we have systems that are at the level of an ML PhD graduate. And we might get them sooner, but I'm just making this, I think, fairly weak claim of at least a 5% chance at this date of this happening. But you might well object to this approach and say, well, we don't really know how all this effective compute stuff works. Maybe you need to throw 20 more orders of magnitude of compute in order to see any real progress. I think that we're still seeing benefits from throwing in compute, and there's no reason to expect that this trend would just suddenly stop, in the next year. But fine, if you don't like this style of argument, we'll look at a totally different style of argument for reaching, I think, a very similar conclusion. So let's go back to those 3 drivers of AI progress, and let's talk more about hobbling and unhobbling models. So imagine that you turn up at a new job, you just got your employment contract, and you didn't actually have the company you're working for, let's say they're a stealth startup, and there's no information about them online at all. You don't really know what you're supposed to be doing. You don't know what they're working on internally. You just turn up, you've got the contract, and you walk in on day 1. The company doesn't have any internet. You can't look anything up. You're not allowed to look up anything at all. You have to just do the job that's being asked of you without searching for anything. And then what's more, super weird, but the keyboard that they give you doesn't have a backspace. And so you have to write everything perfectly. You can't go back and edit anything. You have to produce all the text in linear order without making any mistakes, right? You're also not allowed to run any code. If you want to test code that you've written, you have to hand it off to someone else, and they'll come back to you and give you a fairly weak description of what the error message they got was. You have to give it to another employee to test it. And finally, every hour you black out and forget what happened more than an hour ago, right? I think most of us would probably struggle at a job like this. and probably struggle to do anything useful. But this essentially describes the situations that language models were in circa 2022, when all they had was the chat interface, right? You can't look anything up, so all the facts that you produce have to come from your head, have to be things that the model already knows. You can't edit things that you've said. You have to produce tokens one by one autoregressively. You can't think first before you produce tokens. You can give people code snippets and hope that they come back to you and tell you what's wrong, but often they'll give you pretty bad instructions in terms of what went wrong, and your context window is pretty limited. And since then, we've made significant progress in unhobbling the models by removing these restrictions. Now, if I interact with ChatGPT or Claude, I will get the option to enable web search and allow it to go and look at things. Now I can give it access to my Google Drive so it can see all my different documents and read to give me context, right? So it's no longer the case that these models have zero context about the situation they're dropped into. The models still sample autoaggressively, but now have thinking attached. So they can reason and do lots of messy back and forth with themselves and then produce the answer afterwards. They no longer have to be perfect on the first try without making any mistakes. And the context window is getting much, much larger, and they're being enabled with memory capacity that enables them to maintain coherency over a much longer period of time, right? So all of this progress is in unhobbling the models. I think a lot of people didn't realize when they first started interacting with these systems and saying, well, I asked it some questions and it made some basic factual errors, was that if they were asked about those questions and not able to look anything up, they'd probably also make factual errors, right? Most of us, when we aren't an expert in a domain, need to go and look things up. And even then, sometimes in our domain of expertise, we still need to search for things. And so when you're interacting with these models at first, you're interacting with the model essentially in these positions, massively hobbled. And we've made a lot of progress in removing these restrictions and empowering the models to get the full capabilities out of them. So unhobbling progress refers to unlocking the latent capabilities of the models by augmenting them appropriately. And I'll count in this the sort of basic pipeline of supervised fine-tuning and RLHF that we came up with. Better prompting techniques, so the discovery of chain of thought prompting and reasoning and few-shot prompting. And then everything that we covered in the agent architectures lecture. So all of that stuff. So memory, planning, and tool use, all of this to actually get useful work out of the models. So now let's just straight look at the thing that we're interested in, which is economically valuable labor. I covered this paper in the lecture on evaluations, but to sort of summarize the results, what they're looking at here is the time horizon over which models can perform tasks with about a 50% accuracy. And it's a time horizon for human labor, not the model. The model often does the task significantly faster, but it's how long does a human take to do this task? And you're looking at whether models are capable of doing tasks that are that length yet. And what they're plotting here is model release date, so the date at which the models were released, against the time horizon, which can roughly be considered of how long of a task is the model coherent over. And currently, frontier models are coherent over around an hour time frame, which we're getting here. But importantly, again, the important thing to notice is the y-axis is logarithmic, that this increase is an exponential increase of roughly, with a doubling time of 221 days, which is 7 months. So roughly every 7 months, the horizon over which models can perform tasks coherently doubles, right? And we can extrapolate out to how long is it going to be until the AI systems can do tasks coherently with a 50% accuracy that take human experts a month to complete, right? And we see that looking at the estimates that we had before, we get a wide range of uncertainty, but most of it is concentrated, depending on the different methods you use for doing your sensitivity analysis. But most of the mass is concentrated around 2030, with error bars between 2029 and 2031, right? And so if this trend continues to hold, you would expect that by mid-2030, which is here, models should be able to coherently perform tasks with about a 50% success rate that take roughly 2 months for a human expert to perform. So any machine learning research task that you could give to an ML graduate that would take them 2 months to do, right? Which includes just, come up with better architecture, right? Come up with a better training regime, right? Anything like that, you expect models to be able to do with roughly a 50% success rate. And again, this is conservative because if you limit yourself to only looking at recent history, so recent 2024 to 2025 trend, the rate is actually much higher, and you would expect to see this kind of thing by 2028 instead. So again, we're going to take the conservative one and say, well, mid-2030, this is what I expect to see. So in terms of developments of AI agents, by mid-2030, if this trend continues to hold, you'd expect to see AI systems that, with a roughly 50% success rate, they can autonomously pursue ML research tasks, which usually take a researcher, an expert in their field, 2 months to complete. And the less conservative number is early 2028, but we'll restrict ourselves to the far-off distant future of mid-2030. Yeah.
Was there any comment made in that original study about the length of time it would actually take the AI itself to do these tasks?
No, so that's an excellent question. So remember that the task lengths for an expert human, I think that the AIs generally perform the tasks much faster than humans do. They write text much faster, they can write code much faster, they can debug that code much faster. But no, they don't actually comment on what the ratio of how long it takes humans to do the task and how long it takes the AIs to do the tasks when they're successful is. And I'd be very interested to learn that. So again, the only thing I really want you to take away is here's a completely different line of argument that rests on a different kind of empirical pattern that we're seeing in the data, that there is at least a 5% chance that by mid-2030, we have AI systems that operate at the level of ML PhD graduates, at least for 2 months, right? Okay, so having presented like 2 distinct arguments for why it's very plausible that you should have some small amount of probability mass on this outcome, now I'm going to talk about why this outcome matters, why it matters when we reach the point of having AI systems that can automate ML research work. So what's significant about this? So suppose that you're an AI company, you're OpenAI or Anthropic, and you have internally an AI that is capable of doing ML research. What do? Well, you automate your own internal R&D, right? You essentially can spin up thousands of copies of this AI system and get each of those AI systems to do AI research. And then all of the research they produce then goes back into training your next model, which is smarter and better, and then can automate more of your process, right? So as your current AI system creates smarter AI systems, those systems can do better research, creating yet smarter systems, and so on and so forth, right? So this is a positive feedback loop. The smarter your system is, the more research you can get out of it. The more research you can get out of it, the smarter, the better you can train your models, the smarter they become, the better research you can get out, right? And so on and so forth. And so this positive feedback loop was coined, or the terminology for it was coined by I.J. Good, and it's an intelligence explosion. The idea being that you keep recursing and improving, and the improvements make you better at recursing, and so on. And this could very quickly lead to a super intelligent system, so a system whose capabilities vastly exceed that of any human. Right? This is not a hypothetical thing of, oh, maybe the labs would think to do this, but they'll probably be happy just automating away various jobs. Instead, this is explicitly what they are aiming for internally. This is from an essay written by Sam Altman, CEO of OpenAI. And in the essay, which is Moore's Law for everything, and in the essay, this is a quote: "This technological revolution is unstoppable, and a recursive loop of innovation, as these smart machines themselves help us make smarter machines, will accelerate the revolution's pace." Right? So this idea that we can train a frontier model that can do AI research, that will then automate a large part of our R&D, enabling us to train a better model, which can then automate more of the R&D and produce better research, and so on, is explicitly the aim of many of these companies. This is what they are going to try to do. Okay, So having presenting these visions of why we would expect to see significant, why we expect to see systems get to this level by mid-2030, and present an argument for why you should think there's at least a 5% chance that this will happen. And now I'm going to cover various objections you might have to these arguments, or that I've heard before from people. So one is that, well, scaling these models up, just getting bigger and bigger models, won't we just hit data limitations? These models are already trained on a sizable fraction of the internet. Is there really enough data to train a model that's, 10,000 times larger? So here are some counter arguments to this point. One, you can make really efficient use of data through some methods, such as reinforcement learning. So here's a really efficient way to make use of a maths textbook. Every time you come across a theorem statement, instead of just SFTing, so training on the proof of it, instead, you just ask the model to do reinforcement learning until it finds a proof itself, right? There's a much more efficient use of that data than just training on it by itself, right? Instead of training on code snippets that do certain things, you give the model a doc string that defines the input-output functionality, and then you get the model to generate the code itself through reinforcement learning. So provided you're creative, you can get a lot more out of the data itself than just training on it in a standard way. But even if we don't do anything like this, there's also synthetic data generation, right? Which it seems works fine. It's not a massive problem to just have large chunks of synthetic data in your training set. So it seems like this is another way that you can get around potential data limitations. The other point to make is that algorithmic progress and unhobbling progress don't necessarily require significantly more data. That you can make a lot of progress just unhobbling and algorithmic progress for the models without using larger and larger data sets. Another point that I don't have written here, but is also important to consider, is that in recent years we've seen progress from inference time compute scale up, where you can have a model of a certain capability, and if you let it think for 10 times as long, you get better answers out of it than if it thinks for 10 times fewer tokens. And so this again doesn't require any more data. Once you have the model, you get to choose how long you want to run it for, and you can just run it for 10 times as long, 100 times as long, 1,000 times as long. And provided you have that compute scale up, which historically we've seen, you're going to be able to get better performance out of the models through that. Was there a question? The next objection that you often hear people give is power consumption limitations. So the GPT-4 cluster requires roughly 10 megawatts of power to run. And if you scale this up by 2 orders of magnitude, so you have a cluster that's 100 times larger, that's 1 gigawatt, which is roughly the power consumption of a nuclear power plant. And you might well wonder, can you actually sustain these trends? Can you actually support clusters getting this large? Here are some responses to this. We might have more specialized hardware that brings the compute per watt, I should say upwards. So the amount of compute you can get, the energy consumption of the hardware might fall. And the more relevant thing is that if governments clock on to how big a deal AI is, they may be willing to invest large amounts of money in providing the power necessary for these very large-scale compute. This is often called a Manhattan Project for AI. And last year this was a hypothetical of maybe governments will choose to invest large amounts of money in the energy infrastructure necessary for AIs. And now it's no longer hypothetical because we just have Stargate and they just have done this, right? And again, even if compute just completely stalls, even if we just make zero progress on compute, there's still algorithmic and unhobbling progress, which doesn't require any more compute to make. Here's a tweet from the US Department of Energy. AI is the next Manhattan Project, and the United States will win. United States flag emoji. So I feel pretty confident in making the claim, yep, governments will be willing to invest large amounts of money if they believe that doing so will get them a superintelligence, right? If that's the bargain, right? You give me control of a nuclear reactor, and I give you something that's vastly smarter than all living humans. That's a good bargain to many governments, and as soon as they realize that, these limitations that come from maybe there's just not enough power will go away, right? The final objection is to the idea of an intelligence explosion to begin with. The idea that you could recursively self-improve in a way that would matter, that would allow you to keep getting smarter and smarter until you reach something that was smarter than all humans. So maybe this feedback loop, this positive feedback from automated AI R&D fizzles out rather than exploding. Here's why I don't think this is true. One, AI as a field is currently full of low-hanging fruits. It is possible for people to make progress in AI with very little experience. It does not look like a mature science, like, for example, quantum mechanics or theoretical physics, where in order to make any progress at all, you require an entire undergrad in the subject, and then a master's, and then maybe like a year or two of doctoral training before you can do anything substantial at all. And most people are fundamentally confused about what there even is to do and how to make progress. Instead, you can get an undergrad who has a maths background and do an internship over the summer and get a paper out of it, which advances the state of the field, right? So it's currently full of low-hanging fruit, and I very much doubt that by 2030 we will have completely exhausted this supply. Another point to make here is that, okay, but it's not just you have your intelligent system and it just runs itself once, and you have one copy, and it's equivalent to just hiring one more employee, right? It is instead, if you have the money, if you have the compute resources to train this model, you have the compute resources to run 1 million copies of it in parallel at the same time, right? So you're not just getting one new employee, you're getting 1 million. And even if they are, not as good as the best OpenAI employees, the best OpenAI employee has finite time and operates, in series. They can't just spawn up additional copies of themselves. So even if they're only as useful as like an intern, you can run 1 million copies, that's quite useful. And then the other point about, which comes back to why I don't think we're going to exhaust the low-hanging fruit, is because we still lack quite fundamental understanding of how lots of things in deep learning work. I made a big deal of this in the scaling laws lecture, that we just don't understand where these laws come from. It seems quite plausible that if you could discover where these come from, you could do a whole bunch of other really useful things to advance your capabilities and get more use out of your training. It just seems like there's lots of mysteries within deep learning, lots of things we don't understand, and you could just throw AI researchers at these and make significant progress, and then this would, again, allow you to recursively self-improve. So now I'm going to talk about what the implications of there being a superintelligence are. So in 2017, there was an attack on the NHS in the UK. It was a ransomware attack from a virus called WannaCry, and it essentially crippled the entire NHS for a day, like all of the digital infrastructure that it had. And now I want you to imagine that there is an adversary of some kind, whether it is a foreign state actor who has access to a superintelligent AI, or a superintelligent AI that has gone rogue and escaped confinement, who for some reason wants to shut down digital infrastructure of a country, perhaps because that country is trying to eliminate it. The world that we live in is reliant upon the digital infrastructure that we have, right? So the medical system, the distribution of food, supply chains for all our goods, the ability to pay for things, right? I have £5 of physical money on me, and that's it, and no other physical money. My ability to exchange money for goods and services is based on digital infrastructure, right? And also just basic communication. I have for many people in my life whose addresses I don't know, I have very little way of getting in contact with them beyond digital communication of some kind. And the government's ability to get in contact with me at a short notice because, for example, there is a catastrophe of some kind is again based on digital infrastructure. If all the digital infrastructure went down, it would be very difficult for the government to coordinate a nationwide response to some catastrophe of some kind. So if you have a superintelligent system that is capable of launching superintelligent cyber attacks, So finding zero-day vulnerabilities in software that have never been exploited before at a rate much, much faster than any human team can, and in parallel, because you can run many copies of it at the same time, then it becomes very easy to shut down an entire digital infrastructure of a country if you wanted to. Pathogens we encounter on a day-to-day basis, even those that cause pandemics like COVID, are not optimized for lethality, right? They are built by natural selection. If you optimize for lethality, you probably kill everything around you. You can also only make small local steps in sort of gene space, right? You can't just jump from here to here. There's lots of constraints on what natural selection will churn out, and the pathogens we encounter are not optimized for killing everyone. But if you can build models that are, if you're very, very intelligent, if you're super intelligent, and you're much better at ML than any human, and you're capable of building models that can predict things about viral structures that no human can predict, then you can tailor-make a pathogen for mass destruction if you want to, right? And if you can create these pathogens easily, and you can create cures for those and give them out locally to people within your country or people that you want to, but not by people in an adversary country, then it's very easy to do mass devastation of some kind with some bioweapon that's much more lethal than anything that's been developed so far. Finally, technological superiority gives significant military advantages. If you have tanks and your adversary doesn't, you will probably be better off. If you have nuclear weapons, then if your adversaries do not, it's game over for them. There's nothing they can do at that point if you can develop nukes and they can't, right? And all this technological development can include better sensors, better processing of strategic information, novel weapons, right? And it can also just be the development of lethal autonomous weapons. So drones that can act independently of any human oversight with strategic vision and targeting systems. Right? If you're super intelligent, you can solve robotics. Robotics is not that hard. It's a machine learning problem. You can solve it, and then you can build lethal autonomous weapons very easily. And if a hostile nation builds these weapons, this might not go well, right? If they have a significant military advantage. A lot of the modern geopolitical relationships are built on the fact that if you go to war, you will lose people too, right? If you are not going to lose people, then the calculus changes a lot, right? If you can deploy a lot of lethal autonomous weapons that they just cannot counter, the calculus changes. The final thing I'd like to stress is that we currently do not know how to build safe superintelligence, and there are many problems to being able to do so. The safeguards that we built in against misuse, against some adversary actor taking the model and using it to do something we don't want them to do, can be easily undone, either with jailbreak attacks or with fine-tuning, right? Specifying the goals that we want the system to pursue in the first place, specifying actually how we want the system to behave, is very hard. It's usually subject to Goodhart's law, where you give something that sounds good, but then when optimized for thoroughly, doesn't actually result in the behavior that you want. It's very hard to see how optimizing the objective will actually play out in the real world. Moreover, even if you do specify the goal that you want and you do it perfectly, and Goodhart's law isn't a problem for some reason, that doesn't actually guarantee that the model learns that goal, right? The model may learn a different internal goal. We covered in lecture 9 goal misgeneralization. Models that appear aligned while having the wrong internal goal might be impossible to train them out, or very, very difficult, right? This is deceptive alignment and alignment faking we saw in lecture 11, that sometimes models can strategically pretend to be aligned with the objectives that we give them until they are in a deployment situation, in which case they can defect and pursue whatever goals they have internally that are different from the goals that we have. And finally, the reward signals that we give can be hacked, right? And so again, it's not necessarily the case that just because you've written down a reward function that you think will lead to the behavior you want, you will actually get the behavior that you want out of the system. But suppose that isn't a problem. So suppose that we solve all those issues. So we find out how to align models, we find out how to do it robustly, we find out how to prevent them alignment faking, we overcome Goodhart's law. What then? So what's the good ending? Well, the good ending is that if you get an aligned superintelligence, then by default, if nothing further is done, this will just result in massive power concentration. So in particular, the value of human intellectual labor drops to close to nothing. If there's AIs that are cheaper than humans to maintain and smarter than humans, there is no reason you would employ a human to do any intellectual labor. Hiring an AI as a drop-in remote worker will almost always be preferred to hiring a human for many reasons, the principal one being cost. And without specific countermeasures, this will just lead to massive concentration of wealth among existing capital holders who now have a way to convert capital not just into the means of production, but into labor itself, and those who control the ASI. And if the ASI is controlled by a government as opposed to a private corporation, then it could very easily be used to lock in a form of authoritarianism. If you have a system that's capable of processing vast amounts of information and can build new technology for surveillance, for policing, anything you want, again, it's very hard for people to resist if the government itself has lethal autonomous weapons that they can deploy to roam the streets. Right? So an ASI controlled by a government could easily be used to lock in a form of authoritarianism. What can you do? So if you've enjoyed these lectures and you find the argument made in this lecture that within the next 6 years, so by mid-2030, there's a 5% chance at least of some kind of intelligence explosion happening within the lab, and that currently we are unprepared for such an intelligence explosion to happen, both at a technical level, we do not know how to align these models, and at a societal level, we are not robust or resilient to those models being developed. What can you actually do? You can begin by learning more. So this was an introductory course we put on. If you found it interesting, you want to learn more, I can recommend the Blue Dot Impact's AI Safety Fundamentals course. It's sort of the first thing most people encounter. ML for Good is a fantastic organization that I've worked with before. I can thoroughly recommend. They do both technical AI safety and AI governance camps. And the Center for AI Safety has an AI Safety, Ethics, and Society course. If you are in a position to do technical research on these problems, then you can also try to upskill and begin doing that kind of research. There's the MATS program, which is the most prestigious and generally effective one of these programs. It's full-time for 10 weeks. If you don't have the time for a full-time program, there's also Mars, which is a program run locally here in Cambridge, which is part-time, 8 hours a week. And there's Arena, which focuses just on technical skills. Finally, you're very welcome to reach out to us if you'd like to chat further. I'd like to thank everyone for coming to the course, and also thank my co-lecturers who will come up now. Thank you very much, everyone, for coming.